Hello there, and welcome to Sleep Knowledge. If you're looking for something relaxing, thoughtful, and quietly full of wonder to help you fall asleep, you found the right place. Tonight, we'll be drifting gently through the vast reaches of space, not as a textbook lesson, but as a quiet exploration of the cosmos designed to ease your mind and help you rest. From the burning heart of our sun to the icy reaches beyond Pluto, from storms that dwarf continents to silences deeper than any ocean, it's a story told in light and darkness, in gravity and time, and told softly just for you. If you enjoy relaxing science videos like this made to help you unwind or fall asleep, feel free to like the video and subscribe to Sleep Knowledge. It helps more people find their way to this kind of calm, thoughtful science, and I'd love to hear where in the world you're listening from tonight. Whether you're in Singapore or Stockholm, Lima, or London, you're welcome here. So settle in, let your body get heavy, and let's begin. Picture our sun, the star at the center of everything we know. It sits there 150 million kilometers away, massive beyond comprehension. Over 99% of all the mass in our solar system belongs to the Sun. All the planets, all the moons, all the asteroids and comets combined make up less than a single percent of what exists here. In a very real sense, we live not in a system of planets, but in the domain of a star, with everything else simply orbiting in its light. This isn't meant to be unsettling. It's simply scale. The universe operates on time scales and distances that dwarf human concern. And there's something oddly calming about that. Your worries, your to-do lists, your racing thoughts, all of it exists in a universe so vast that perspective itself becomes a form of peace. The sun is not eternal. Nothing is. Someday, billions of years from now, it will swell into a red giant, growing so large it may consume the inner planets. Mercury will likely vanish first, then Venus. Earth's fate is less certain. It may survive, scorched and lifeless, or it may be pulled into the expanding envelope of our dying star. But this will not happen for 5 billion years. That's longer than Earth has existed, longer than multicellular life has walked, swam, or crawled. It's a span of time so immense that it loses meaning in the human mind. And that's the point. Time, at cosmic scales, doesn't rush. It simply unfolds, slowly, inevitably, without hurry. The sun's light takes about 8 minutes to reach us. That means if the sun were to suddenly vanish, we wouldn't know for 8 minutes. We'd continue to orbit in absence, living in borrowed light from a star already gone. Of course, this will never happen. Stars don't vanish. They burn through their fuel in predictable, patient ways. But the thought itself is a reminder of how distant everything truly is, how much empty space exists between objects, how silence and stillness are the default state of the cosmos. Even the light we see is old. Photons born in the sun's core take thousands of years to reach its surface, bouncing from atom to atom in the dense interior before finally escaping into space. By the time sunlight touches your skin, it has already traveled an unimaginable journey. You are warmed by ancient light, energy that began its life long before human civilization existed. The sun is not calm, though. Its surface roils with convection currents, vast columns of plasma rising and falling like slow-motion ocean waves. Occasionally, magnetic fields twist and snap, releasing bursts of energy called solar flares. These flares can carry the energy of billions of nuclear bombs, though they dissipate harmlessly into space. Most of them never reach us. And even when they do, Earth's magnetic field acts as a shield, deflecting charged particles and protecting the surface below. Sometimes, though, particularly strong solar storms interact with our atmosphere, creating auroras, shimmering curtains of green and red light near the poles. These are reminders that we live inside a star's influence, bathed in its wind, shaped by its moods. Yet life has thrived here for billions of years, adapting to the rhythms of solar activity, the cycles of day and night, the predictable dance of seasons. We are children of this star. Every atom in your body heavier than hydrogen was forged in the heart of a star that lived and died before our sun was born. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in the furnace of stellar fusion, then scattered across space when that ancient star exploded. You are, quite literally, made of stardust. Let's move closer to home now. Mercury, the smallest planet, orbits nearest to the Sunday. It's a world of extremes. During the day, surface temperatures soar to over 400 degrees Celsius, hot enough to melt lead. At night, with no atmosphere to trap heat, temperatures plunge to minus 180 degrees, a swing of more than 600 degrees between day and night, and yet Mercury endures. It has been doing this for over 4 billion years. Day after scorching day, night after freezing night, locked in its elliptical orbit, slowly rotating. A single day on Mercury lasts 59 Earth days. A year lasts just 88 Earth days. This means a Mercurian day is longer than its year, a strange inversion of time. There's something almost meditative about that. Time doesn't work the same way everywhere. A day here is not a day there. Duration is relative, and perhaps your own sense of time, the feeling that hours drag or fly, that weeks blur together, perhaps that's just as valid as any planetary rotation. Mercury has no atmosphere to speak of, just a thin exosphere, barely more than vacuum. This means there's no weather, no wind, no rain, no sound. If you stood on Mercury's surface, the silence would be absolute, not the silence of a quiet room, but the silence of space itself, where there is no air to carry vibrations, no medium for sound to travel through, just light and shadow, heat and cold, and the distant sun overhead, 3 times larger than it appears from Earth. Venus comes next, our so-called sister planet. It's nearly the same size as Earth, formed from the same primordial materials, but there the similarities end. Venus is a cautionary tale about runaway greenhouse effects, a world where carbon dioxide trapped heat until the surface became an oven. The atmosphere on Venus is so thick, so dense, that standing on its surface would feel like being 900 meters underwater on Earth. The pressure alone would crush most structures, and the temperature is even more extreme than Mercury, despite Venus being farther from the Sunday. At 465 degrees Celsius, it's hot enough to melt lead, zinc, and tin. Hot enough that early Soviet probes sent to explore the surface lasted only minutes before succumbing to the heat and pressure. And it rains there, though not water. The clouds of Venus are made of sulfuric acid. Droplets form, fall partway through the atmosphere, then evaporate before reaching the ground, creating ghostly rain that never lands. A day on Venus lasts 243 Earth days, and it rotates backward relative to most planets, slowly spinning in the opposite direction. Another reminder that the rules we take for granted here don't apply everywhere. Venus wasn't always like this. Billions of years ago, it may have had oceans, a milder climate, perhaps even conditions suitable for life, but something went wrong. The sun's energy, trapped by thickening clouds, turned Venus into a furnace. It's a reminder that planets are not static, they change. Atmospheres thicken or thin. Magnetic fields strengthen or fade. Stability is temporary, but temporary, on planetary timescales, can still mean billions of years. Earth, our home, is next. A pale blue dot in the vastness, unique in ways we're still discovering. We have liquid water, a protective magnetic field, an atmosphere rich in oxygen, and a moon large enough to stabilize our axial tilt, giving us predictable seasons. None of this was guaranteed. It's the result of countless variables aligning just so. We orbit at the right distance from the sun, in what astronomers call the habitable zone. Not too hot, not too cold. Our planet's core is molten, generating a magnetic field that shields us from solar wind and cosmic radiation. Without it, our atmosphere would have been stripped away long ago, the way Mars lost most of its air. Earth is constantly bombarded by space debris. Meteoroids, bits of rock and metal, enter our atmosphere every day. Most are small, burning up as meteors, the shooting stars we sometimes wish upon. Larger objects are rarer, but they do strike. Around 65 million years ago, an asteroid roughly 10 kilometers wide hit what is now the Yucatan Peninsula, triggering mass extinction. It reshaped life on Earth, ending the age of dinosaurs and allowing mammals, and eventually humans, to rise. This isn't a threat to lose sleep over. Such impacts are extraordinarily rare on human timescales. The odds of a civilization-ending asteroid strike in your lifetime are vanishingly small, and we're watching now. Astronomers track near-Earth objects, mapping their orbits, calculating risks. We're no longer blind to what's out there, and what's out there is mostly empty space. The solar system is far more emptiness than matter. If you scaled the sun down to the size of a basketball, Earth would be a peppercorn about 26 meters away. Neptune would be a slightly smaller peppercorn over 800 meters distant. The space between is just that. Space, silence, darkness. This emptiness is part of what keeps us safe. Collisions are rare because there's so much room to miss. Objects drift past each other, separated by distances too vast to easily comprehend. Even in the Asteroid Belt, between Mars and Jupiter, where millions of rocky fragments orbit, the average distance between asteroids is enormous. You could fly through it and likely never see one. Mars, the red planet, has fascinated humans for centuries. It's cold and dry now, a desert world with a thin atmosphere, but it wasn't always like this. Billions of years ago, Mars had a thicker atmosphere, liquid water on its surface, perhaps even oceans. River valleys carved by ancient floods still scar the surface. Deltas and lake beds, now dry, hint at a wetter past. But Mars is small, about half the diameter of Earth. Its core cooled faster, and without a molten interior to generate a magnetic field, solar wind gradually stripped away its atmosphere. What remains is thin, mostly carbon dioxide, with surface pressure less than 1% of Earth's. You couldn't breathe there, and the cold is intense. Average temperatures hover around minus 60 degrees Celsius, though they can rise to a relatively balmy 20 degrees at the equator during summer. Dust storms are common on Mars. Some are local, small whirlwinds that leave spiral traces in the sand. Others grow to engulf the entire planet, turning the sky opaque for months. These storms don't threaten the planet itself. They're just weather, part of the Martian rhythm. And when they pass, the sky clears, revealing a landscape of rust-colored dunes, ancient volcanoes, and canyons, deeper than any on Earth. Olympus Mons, the largest volcano in the solar system, rises 22 kilometers above the Martian plains, nearly 3 times the height of Mount Everest. It's a shield volcano, built from countless slow lava flows over millions of years. It's no longer active, but its sheer scale is humbling. A mountain so tall you could walk up its slopes for days and barely notice the incline. From the summit, the curve of the planet would be visible. You'd be standing above most of the atmosphere, looking out at a world of red sand and black sky. Valles Marineris, a canyon system stretching over 4,000 kilometers, dwarfs Earth's Grand Canyon. If placed on Earth, it would span the width of the United States. These features weren't created quickly. They formed over geological time, shaped by tectonic forces, water flow, and slow erosion. Everything on Mars moves slowly. Time doesn't hurry there. Beyond Mars lies the Asteroid Belt, a ring of rocky debris orbiting the Sun between Mars and Jupiter. These are remnants from the solar system's formation, material that never coalesced into a planet, likely due to Jupiter's immense gravity disrupting the process. There are millions of asteroids, ranging from tiny pebbles to Ceres, a dwarf planet nearly 1,000 kilometers across. Despite their numbers, the total mass of the asteroid belt is less than our moon. They're spread out over an enormous volume of space. If you were traveling through the belt, you'd likely need a telescope to spot the nearest asteroid. They're not densely packed like in science fiction. They drift, separated by thousands or millions of kilometers, orbiting the Sun in quiet isolation. Collisions do happen, but they're slow, gentle taps more often than violent impacts. When asteroids collide, they fracture, creating smaller fragments that continue orbiting. Some of these fragments eventually migrate inward, becoming the meteorites that occasionally fall to Earth, carrying clues about the solar system's early history. Jupiter dominates the outer solar system. It's massive, over 300 times the mass of Earth, and made mostly of hydrogen and helium, more like a star than a rocky planet. If Jupiter had been about 80 times more massive, it might have ignited fusion in its core, becoming a second sun. As it is, it remains a planet, though it emits more heat than it receives from the Sun, still cooling from its formation over 4 billion years ago. Jupiter's atmosphere is a churning maelstrom. Bands of clouds race around the planet at different speeds, creating turbulent boundaries where storms form. The Great Red Spot, a storm larger than Earth, has been raging for at least 400 years, possibly much longer. It rotates counterclockwise, completing one turn every 6 days, fueled by heat rising from Jupiter's interior. This storm isn't dangerous to anyone. It's just weather on a planetary scale, a natural consequence of Jupiter's size and composition. It will eventually fade, perhaps in another century or two, replaced by other storms that will rise and fall in turn. Jupiter's weather patterns have been shifting for billions of years, and they'll continue long after humanity is gone. Jupiter has at least 79 known moons, maybe more. 4 of them, the Galilean moons, are large enough to be worlds in their own right. Io, the innermost, is the most volcanically active body in the solar system. Tidal forces from Jupiter and the other moons knead Io's interior, keeping it molten. Lava erupts constantly, resurfacing the moon and making it one of the youngest surfaces we know of. Europa, the next moon out, is covered in ice. Beneath that ice, perhaps 10 to 15 kilometers thick, there may be a global ocean, kept liquid by the same tidal heating that affects Io. If that ocean exists, it could contain more water than all of Earth's oceans combined. And where there's liquid water, there's the possibility of life, though we don't yet know. Ganymede, the largest moon in the solar system, is bigger than Mercury. It has its own magnetic field, the only moon known to have one. Callisto, the outermost Galilean moon, is heavily cratered, its surface ancient and unchanged for billions of years, a record of every impact it has endured. These moons orbit Jupiter in a delicate dance, locked in gravitational resonance. For every 4 orbits Io makes, Europa makes 2, and Ganymede makes 1. This synchronization is not coincidence. It's the result of gravitational tugs over millions of years, a system that has found balance. Jupiter also acts as a guardian of the inner solar system. Its immense gravity pulls in comets and asteroids that might otherwise strike Earth. Some impacts, like Shoemaker-Levy 9 inches 1,994, have been observed directly. The comet broke into fragments and slammed into Jupiter's atmosphere, creating dark scars visible from Earth. Without Jupiter, Earth might have been hit by far more large objects over its history, possibly preventing complex life from ever developing. But this protection isn't intentional. Jupiter doesn't care. It simply exists, and its gravity shapes the orbits of everything nearby. There's no purpose, no design, just physics playing out over billions of years. Saturn, the jewel of the solar system, is known for its rings. They're made of ice and rock, ranging from tiny grains to house-sized boulders, all orbiting Saturn in a thin, flat plane. The rings are bright, reflecting sunlight, and they're surprisingly thin. Though they stretch hundreds of thousands of kilometers wide, they're often less than 10 meters thick in places. The rings aren't permanent. They're slowly spiraling inward, pulled by Saturn's gravity and eroded by micrometeorite impacts. In another 100 million years, they may be gone, leaving Saturn a plain, ringless planet like Jupiter. For now, though, they endure, a reminder that even the most beautiful structures are temporary. Saturn itself is similar to Jupiter, a gas giant made mostly of hydrogen and helium. It's less dense than water. If you could find an ocean large enough, Saturn would float. Its atmosphere has winds exceeding 1,800 kilometers per hour, among the fastest in the solar system, driven by heat from the planet's interior. Like Jupiter, Saturn has many moons. Titan, the largest, is bigger than Mercury and has a thick atmosphere, mostly nitrogen. It's the only moon in the solar system with substantial air, and it has lakes and rivers on its surface, though they're made of liquid methane and ethane, not water. Rain falls there, carving channels and pooling in basins. It's a strange, cold world with surface temperatures around minus 180 degrees Celsius, but it's geologically active with weather and seasons. Enceladus, another moon, is small but fascinating. It has geysers near its south pole that shoot water ice into space, creating one of Saturn's faint outer rings. This suggests liquid water beneath the surface, formed by tidal forces. Like Europa, Enceladus might have an ocean. And where there's water, the question of life always arises, though answers remain elusive. Uranus and Neptune, the ice giants, orbit in the cold outer reaches of the solar system. Uranus is tilted on its side, rotating at a 98-degree angle relative to its orbit. This likely resulted from a massive collision early in the solar system's history, a violent event that left the planet spinning like a top knocked over. Because of this tilt, Uranus has extreme seasons. Each pole experiences 42 years of continuous sunlight, then 42 years of darkness. Imagine a winter that lasts longer than a human lifetime. Yet the planet endures, its atmosphere calm and cold, with temperatures dropping to minus 224 degrees Celsius. Neptune, the farthest planet, is a deep blue, colored by methane in its atmosphere. It has the fastest winds in the solar system, reaching 2,100 kilometers per hour. Storms appear and vanish without warning, dark spots that drift across the planet's face, then dissipate as mysteriously as they formed. Neptune is so far from the sun that it receives less than 1% of the sunlight Earth does, yet it's geologically active, emitting more heat than it receives. This internal heat drives weather and atmospheric dynamics, creating a planet that's dynamic despite its distance and cold. Triton, Neptune's largest moon, orbits backward, opposite the planet's rotation. This suggests it wasn't formed alongside Neptune but was captured, perhaps a Kuiper Belt object pulled into orbit by Neptune's gravity. Triton's surface is covered in nitrogen ice, and it has active geysers, plumes of nitrogen gas erupting from beneath the surface. It's also slowly spiraling inward. In a few 100 million years, it will be torn apart by Neptune's gravity, forming a ring system around the planet. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies stretching billions of kilometers into space. Pluto, once considered the 9th planet, is part of this region. It's small, about 2/3 the diameter of our moon, and it orbits in a tilted, elliptical path that sometimes brings it closer to the Sun than Neptune. Pluto's surface is a mix of nitrogen, ice, water ice, and rock. Mountains rise kilometers high, made of water ice as hard as steel at Pluto's frigid temperatures, which hover around -233 degrees Celsius. Its atmosphere, thin and composed mostly of nitrogen, freezes and falls to the surface as snow during Pluto's 248-year orbit, only to sublimate back into gas when it nears the Sunday. Pluto has 5 known moons. Charon, the largest, is so big relative to Pluto that the two orbit a common center of gravity between them, making them almost a double planet. The other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller, irregularly shaped chunks of ice and rock. The Kuiper Belt contains thousands, perhaps millions, of icy bodies. Some are small, just a few kilometers across. Others, like Eris, Makemake, and Haumea, rival Pluto in size. They're remnants from the solar system's formation, material that never coalesced into a planet, left to drift in the cold outer darkness. Comets originate here and in the even more distant Oort cloud, a spherical shell of icy objects that may extend halfway to the nearest star. When gravitational perturbations nudge an Oort cloud object inward, it begins a long fall toward the Sun, heating as it approaches. Ice sublimates, forming a glowing coma and tail that can stretch millions of kilometers. Comets have been observed throughout human history, often interpreted as omens. They're not. They're just ice and rock, following predictable orbits. Some return regularly, like Halley's Comet, which appears every 76 years. Others are one-time visitors, falling in from the Oort cloud, swinging past the Sun, and flying back out into interstellar space, never to return. A large comet impact on Earth would be catastrophic, potentially causing global climate disruption. But such events are rare on human timescales. The last major impact was 65 million years ago, and we're actively monitoring near-Earth objects now. The universe is vast and mostly empty. Impacts are the exception, not the rule. Space itself is almost entirely silent. Sound requires a medium, air or water, molecules vibrating and transferring energy. In the vacuum of space, there's no air, no medium. Explosions, collisions, even the roar of a rocket engine, all happen in absolute silence. Light travels, but sound does not. This silence is profound. It's not the quiet of a library or a forest at night. It's the absence of sound itself. If you could float in space, you'd hear only your own heartbeat, your breathing, the faint sounds conducted through your suit. Everything beyond would be perfectly, utterly still. Exposure to vacuum is immediately dangerous, though not in the way movies depict. You wouldn't explode or freeze instantly. Instead, the lack of pressure would cause the air in your lungs to expand. You'd lose consciousness within 15 seconds as oxygen stopped reaching your brain. Death would follow in about 90 seconds. It's quick, at least, but this will never happen to you. Space is not a place humans wander unprotected. We build spacecraft, suits, shields. We respect the environment and take precautions. The silence and vacuum are facts, not threats. Reminders that space is not built for us. The solar system itself is in motion. We orbit the center of the Milky Way galaxy at about 230 kilometers per second. completing one full orbit every 230 million years. The last time we were in this part of the galaxy, dinosaurs were just beginning to dominate the Earth. The next time we return, the planet will be unrecognizably different. As we orbit, we pass through different regions of the galaxy, areas with varying densities of stars, gas, and dust. Some regions are more crowded, others more sparse. These changes happen slowly, over millions of years, but they can influence the solar system. A nearby supernova, for example, could send a wave of radiation toward Earth, potentially stripping away part of our ozone layer and affecting life on the surface. This may have happened before. Some mass extinctions in Earth's history have been linked to cosmic events, but these are rare, occurring on timescales of hundreds of millions of years. For now, the solar system drifts through a relatively quiet part of the galaxy, undisturbed. Gravity governs everything. It's the force that holds the solar system together, that keeps planets in orbit, that shapes stars and galaxies. It never turns off, never weakens. Everything is always falling towards something. Earth falls around the Sunday, the moon falls around Earth, the sun falls around the galactic center. It's all falling, all the time, in a carefully balanced dance. There's no absolute up or down in space. Orientation is relative, defined only by reference frames. We say the sun is above or below because we choose a perspective, but from another angle, those directions reverse. The universe has no preferred orientation, it simply is. This can feel disorienting. The idea that direction is arbitrary, that there's no fixed point to anchor ourselves to, but it's also freeing. Without up or down, without edges or boundaries, space becomes a place of infinite possibility, where perspective itself is a choice. The solar system has no edge you can point to. It doesn't end at Pluto or the Kuiper Belt or even the Oort cloud. It fades gradually, the sun's gravity weakening, the density of objects decreasing, until eventually you're in interstellar space, the region between stars. But there's no border, no sign marking the transition, just a slow gradient from one domain to another. Rogue planets may drift through the galaxy, worlds ejected from their home systems by gravitational interactions, wandering alone through the dark. Some models suggest there could be more rogue planets than stars, countless orphaned worlds drifting silently through space. Occasionally, one might pass through our solar system, its gravity tugging on the planets, altering orbits slightly. These interactions are subtle and slow. Planetary orbits are stable on human timescales, but can shift over millions or billions of years. Gravitational resonances can amplify small perturbations, leading to chaos. Mathematically, the solar system's long-term stability is uncertain. Given enough time, a planet could be ejected, or orbits could shift dramatically. But enough time means billions of years, far beyond human concern. For now, the solar system is stable. The planets orbit as they have for eons, predictable and steady. The sun itself is slowly changing. It's been burning hydrogen in its core for about 4.6 billion years, and it will continue for another 5 billion. As it ages, it gradually brightens, increasing its energy output by about 10% every billion years. This slow brightening will eventually make Earth uninhabitable, boiling away the oceans long before the sun enters its red giant phase. But again, this is billions of years away. Time enough for life to adapt, to migrate, to change. Time enough for humanity, if it survives, to leave Earth and find new homes among the stars. The sun will not explode. It's not massive enough for a supernova. Instead, it will die quietly, expanding into a red giant, then shedding its outer layers to form a planetary nebula, a glowing shell of gas expanding into space. What remains will be a white dwarf, a dense, cooling ember about the size of Earth, slowly fading over trillions of years. This is the fate of most stars, not violent explosions, but gradual dimming. They burn, they swell, they fade, and in their deaths, they return material to the galaxy, enriching the interstellar medium with elements created in their cores. From this material, new stars and planets will form, continuing the cycle. Cosmic rays, high-energy particles from distant supernovae and other sources constantly bombard the solar system. They strike Earth's atmosphere, creating showers of secondary particles. Most are harmless, deflected by our magnetic field or absorbed by the atmosphere. But over long timescales, they contribute to background radiation, causing DNA damage and mutations. This radiation is part of the natural environment, one of many factors that drive evolution. Life on Earth has adapted to it, developing repair mechanisms for DNA damage. It's not something to fear, just another aspect of living on a planet bathed in starlight and cosmic particles. The Moon, Earth's companion, is slowly drifting away from us. Tidal interactions transfer angular momentum from Earth's rotation to the Moon's orbit, causing it to recede at about 3.8 centimeters per year. Billions of years from now, the Moon will be much farther away, and Earth's day will be longer. Tides will weaken. The Moon's stabilizing influence on Earth's axial tilt will diminish, potentially leading to more extreme climate variations. But this is a slow, gentle process. For now, the Moon remains close, its phases marking the passage of time, its gravity stirring the oceans, its presence a familiar constant in the night sky. Human spacecraft have already left the solar system. Voyager 1 and 2, launched in 1977, have passed beyond the heliosphere, the bubble of charged particles emanating from the Sun, and entered interstellar space. They carry golden records with sounds and images from Earth, messages for any intelligence that might find them. These probes will drift for billions of years, long after the Sun has died, long after Earth is gone. They're monuments to human curiosity, fragile machines carrying stories into the void. They'll never be recovered. They'll simply travel, silent and alone, through the galaxy. Space debris from human activity orbits Earth, remnants of satellites, rocket stages, fragments from collisions. This debris travels at thousands of kilometers per hour. Even a paint flick can damage spacecraft, punching holes in solar panels or cracking windows. Larger pieces pose greater risks. We're tracking this debris, working to minimize future collisions, but space is becoming more crowded near Earth. It's a reminder that even space has consequences, that our actions ripple outward, affecting the environment we depend on. The solar system formed from a collapsing cloud of gas and dust about 4.6 billion years ago. Gravity pulled material together, forming the Sun at the center and a rotating disk of debris around it. Within this disk, particles collided, sticking together, growing into larger and larger bodies. Planetesimals formed, then protoplanets, and eventually the planets we see today. Early Earth was nothing like it is now. It was molten, bombarded by impacts, its surface a hellscape of lava and rock. The Moon likely formed from debris ejected when a Mars-sized object struck Earth, a collision so violent it vaporized rock and sent molten material into orbit. Over time, Earth cooled. Water arrived, delivered by comets and asteroids. An atmosphere formed. Life began, simple at first, then gradually more complex. The story of the solar system is inseparable from the story of life on Earth. Both emerged from chaos, shaped by time and chance into the forms we recognize. Planets migrate. Jupiter, for example, likely formed farther from the Sun and then drifted inward before settling into its current orbit. This migration disrupted the inner solar system, scattering material and influencing the formation of the terrestrial planets. Our current configuration is not the original one. It's the result of billions of years of gravitational interactions, collisions, and adjustments. Stability, in this sense, is an illusion. Everything is always moving, always changing. But the changes are so slow, spread over such immense timescales, that from a human perspective, the solar system seems eternal. It's not. Nothing is. But temporary, on cosmic scales, can still mean billions of years, long enough for stars to live and die, long enough for civilizations to rise, flourish, and fade. Darkness vastly outweighs light. The universe is mostly empty space, cold and silent. Stars and planets are rare exceptions, brief flickers in the immense void. Cold vastly outweighs heat. The average temperature of the universe is just a few degrees above absolute zero, the coldest temperature possible. This isn't depressing. It's simply the nature of things. The universe is not built for comfort. It's indifferent to life, to consciousness, to meaning. And yet here we are, on a small planet orbiting an ordinary star, thinking and wondering and asking questions. The solar system doesn't care about us. It will continue long after humanity is gone. Planets will orbit, moons will drift, the sun will burn, existence will go on, indifferent and patient. But that indifference is also a kind of freedom. There's no cosmic judge, no external pressure. The universe doesn't demand anything of us. We're free to choose our own meaning, to create our own purpose, to decide what matters, and perhaps that's enough, to exist, however briefly, in a universe so vast, to witness the beauty of Saturn's rings, the storms of Jupiter, the silence of space, to know we're part of something larger, even if that something doesn't know we exist. So as you lie here now, beginning to drift, let yourself settle into the stillness. There's no need to hold on to any of this. Just let it wash over you like starlight. Your breath is slowing, your thoughts are softening, and somewhere in the quiet, you're becoming part of the same vast, patient cosmos we've been drifting through. You are not separate from this universe. You are made of it. The atoms in your body were forged in stars, scattered across space, gathered into a planet, assembled into life. Every breath connects you to the same processes that built galaxies and lit suns. And in this moment, lying here in the dark, you are exactly where you're meant to be. Resting, releasing, returning to the rhythm that carried the cosmos forward for billions of years. The rhythm of expansion and contraction, of light and darkness, of beginnings and endings. There's nothing more to learn tonight, nothing more to hold. Just this quiet, this calm, this gentle drifting into rest. Let your body grow heavy. Let your mind release its grip. There is no urgency, no unfinished task. Only the soft pull of sleep, patient and kind, waiting for you to let go. If you happen to still be awake, that's okay too. You can go ahead and watch the next video, or simply lie here a while longer, letting the silence settle around you. But if sleep is finding you now, welcome it, trust it. It's been part of you since the beginning. A gift inherited from the same stardust that built everything you see. Let's drift a little deeper now, into the spaces between the planets, into the phenomena that shape our cosmic neighborhood. There's more to explore here, more quiet wonders to ease you into rest. Consider light itself. We talk about the speed of light as if it's instantaneous, but it's not. Light travels at 299,792 kilometers per second. That sounds fast, and it is by human standards. But in cosmic terms, light is almost sluggish. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun, 8 minutes ago. Jupiter, depending on where it is in its orbit, between 35 and 52 minutes ago. Neptune, over 4 hours ago. By the time light from Neptune reaches your eyes, Neptune has moved. You're seeing where it was, not where it is. This time delay means we never see the universe as it currently exists. We see only the past. The farther we look, the deeper into history we peer. The nearest star beyond the Sun, Proxima Centauri, is 4.24 light-years away. The light you'd see from it tonight left that star over 4 years ago. And if Proxima Centauri suddenly exploded, we wouldn't know for 4.24 years. We'd continue to see it shining peacefully in the night sky, unaware of the distant catastrophe. Time, distance, and light are woven together in ways that defy everyday intuition. This is not cause for anxiety. It's simply the fabric of reality. The universe is patient with information. Nothing happens instantly across distances. There's always delay, always time for things to unfold. Gravity, too, travels at the speed of light. If the sun vanished, its gravitational pull wouldn't disappear immediately. For 8 minutes, Earth would continue orbiting the ghost of a star, held in place by gravitational waves that hadn't yet reached us. Then, suddenly, we'd fly off in a straight line, no longer bound to anything. Of course, this is purely theoretical. Stars don't vanish. The sun is stable, burning steadily, held together by the balance between gravity compressing it and fusion pushing outward. This balance has been maintained for over 4.6 billion years, and it will continue for billions more. The sun's core is unimaginably hot, about 15 million degrees Celsius. At these temperatures, hydrogen atoms fuse into helium, releasing energy. This energy, in the form of photons, begins a long journey outward. In the dense core, photons travel only a tiny distance before being absorbed and re-emitted by another atom. They bounce around, taking a random walk that can last thousands of years. By the time a photon reaches the sun's surface, it has been absorbed and re-emitted countless times. The light that warms your face on a sunny day is ancient, born in the sun's core eons before you existed, finally escaping into space after millennia of wandering. And yet, from our perspective, the sun feels constant, reliable, unchanging. It rises and sets with predictable rhythm, marking days and seasons. We trust it without thinking, and that trust is well placed. The sun is stable on timescales that matter to us. Space weather is another phenomenon worth considering, not because it's threatening, but because it reminds us we live inside a star's atmosphere. The sun constantly emits a stream of charged particles called the solar wind. This wind flows outward in all directions, filling the solar system with a thin plasma. Earth's magnetic field deflects most of this wind, creating a protective bubble around the planet. But sometimes, the sun releases a particularly strong burst, a coronal mass ejection, sending billions of tons of plasma hurtling into space. If one of these hits Earth, it can compress our magnetic field, triggering geomagnetic storms. These storms are usually harmless to people on the ground. The atmosphere shields us, but they can disrupt satellites, affect power grids, and create spectacular auroras. The northern and southern lights, shimmering curtains of green, red, and purple, are caused by charged particles from the sun colliding with atoms in Earth's upper atmosphere. Auroras are most common near the poles, where Earth's magnetic field lines converge, funneling particles downward. But during strong geomagnetic storms, they can be visible much farther from the poles. People in lower latitudes occasionally glimpse them, faint glows on the horizon, reminders that we're connected to the sun by more than just light. The solar wind extends far beyond the planets, creating a bubble called the heliosphere. The boundary of this bubble, where the solar wind's pressure balances the pressure of interstellar space, is called the heliopause. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Even there, billions of kilometers from the Sun, the influence of our star is felt. The heliopause is not a sharp edge but a gradual transition, a region where conditions shift from solar-dominated to interstellar. It's another reminder that boundaries in space are rarely clean. They're gradients, zones of change, places where one environment blends into another. Interstellar space itself is not truly empty. It contains gas, mostly hydrogen, at incredibly low densities. On average, there might be 1 atom per cubic centimeter. By comparison, Earth's atmosphere at sea level contains about 19 molecules per cubic centimeter. Interstellar space is a better vacuum than anything we can create in a laboratory, but it's not nothing. That thin gas, spread across light years, adds up. Between stars, clouds of gas and dust drift, sometimes collapsing under their own gravity to form new stars. Our sun was born from such a cloud, and someday, the material it returns to space will contribute to new star formation elsewhere in the galaxy. This cycle of birth and death, of creation and dispersal, has been ongoing for billions of years. Stars form, burn, and die, enriching the galaxy with heavier elements. Each generation of stars contains more of these elements than the last, slowly changing the chemical composition of the universe. Our solar system is relatively rich in heavy elements, which is why we have rocky planets like Earth. Earlier generations of stars had less material to work with, forming planets that might have been quite different if they formed planets at all. Meteorites, fragments of asteroids that survive the journey through Earth's atmosphere and land on the surface, carry clues about the solar system's early history. Some are billions of years old, unchanged since the solar system's formation. They contain tiny grains of material that predate the Sun, fragments of other stars embedded in the collapsing cloud that formed our solar system. These pre-solar grains are older than anything else we can touch. They survived the death of their parent stars, drifted through space, became part of our solar nebula, and eventually landed on Earth, preserved in stone. Holding a meteorite is, in a sense, holding a piece of another star. Most meteorites are rocky or metallic, fragments from the asteroid belt knocked loose by collisions. But some are carbonaceous chondrites, rich in organic compounds and water. These meteorites may have delivered the raw materials for life to early Earth, seeding the planet with the chemistry that would eventually lead to biology. Life's origins remain mysterious. We know it began at least 3.5 billion years ago, possibly earlier. The exact mechanisms are still debated, but the building blocks, amino acids, sugars, lipids, have been found in meteorites, suggesting they're common in space. This doesn't diminish the wonder of life. If anything, it deepens it. Life may not be a rare fluke, but a natural consequence of chemistry under the right conditions. If that's true, then life might exist elsewhere, on moons, exoplanets, places we've yet to discover. Europa, Jupiter's moon, remains one of the most intriguing candidates. Its icy surface is crisscrossed with fractures and ridges, evidence of geological activity. Tidal forces from Jupiter flex Europa's interior, generating heat. This heat could keep a subsurface ocean liquid, even though the surface temperature is minus 160 degrees Celsius. If that ocean exists, it's been isolated from the surface for billions of years, shielded from radiation, possibly warm and chemically rich near hydrothermal vents on the ocean floor. On Earth, hydrothermal vents teem with life, organisms that don't rely on sunlight but draw energy from chemical reactions. Could something similar exist on Europa? We don't know. We haven't yet sent a probe capable of drilling through the ice, but the possibility is tantalizing, a reminder that life doesn't require Earth-like conditions. It requires liquid water, energy, and chemistry. Those conditions might exist in many places we once thought barren. Enceladus, Saturn's small moon, is another candidate. It ejects plumes of water vapor from cracks near its south pole, geysers that shoot hundreds of kilometers into space. These plumes contain salt, organic molecules, and tiny grains of silica, all suggesting a warm, salty ocean beneath the ice. A spacecraft has already flown through these plumes, tasting Enceladus's ocean without landing. The data suggests conditions that could, in theory, support microbial life. Whether life actually exists there is unknown, but the ingredients are present. Titan, Saturn's largest moon, has a different kind of intrigue. It's the only moon with a substantial atmosphere, thicker than Earth's, mostly nitrogen with traces of methane. On Titan's surface, liquid methane and ethane flow in rivers, pool in lakes, and rain from the sky. This is a world with weather, erosion, and a hydrological cycle, but based on hydrocarbons instead of water. Titan's surface temperature is minus 179 degrees Celsius, far too cold for liquid water. But chemistry still happens. Organic molecules form in the atmosphere, complex compounds that drift down and accumulate on the surface. Some scientists speculate that Titan's chemistry might support a form of life, something radically different from Earth life, using methane as a solvent instead of water. It's speculative, but Titan's environment is unique in the solar system, and unique environments invite unique possibilities. These moons, Europa, Enceladus, Titan, they're not destinations for casual visits. They're distant, cold, and inhospitable to humans. But they're also laboratories, natural experiments in planetary science, showing us the diversity of worlds that exist even in our own solar system. And if such diversity exists here, imagine what exists beyond exoplanets. Planets orbiting other stars have been discovered by the thousands. Some orbit in their star's habitable zone, where temperatures might allow liquid water. Others are massive gas giants, or scorching hot worlds, or frozen ice balls. Each discovery expands our understanding of what's possible. Planets are common. Most stars have them. And among those billions of planets, it seems statistically unlikely that Earth is the only one with life. But we don't know yet. We're still looking, still listening. The search for extraterrestrial life is one of the great questions of our time, and the answer, whatever it turns out to be, will change how we see ourselves and our place in the universe. For now, though, we remain alone, as far as we know. One planet, one species, looking out at the stars and wondering. The moon, Earth's only natural satellite, has been a companion to humanity since before we were human. Early primates saw it, dinosaurs saw it. The first simple organisms on Earth existed under the same moon we see today, though it was closer then, appearing larger in the sky. The moon's formation is dramatic. Around 4.5 billion years ago, a Mars-sized object called Theia collided with early Earth. The impact vaporized rock, sending molten material into orbit. Over time, this debris coalesced, cooling into the moon. This collision reshaped Earth, tilting its axis, stripping away part of its crust, and delivering angular momentum that sped up its rotation. Without this impact, Earth would be a different planet, possibly without the stable climate that allowed complex life to develop. The moon stabilizes Earth's axial tilt, keeping it around 23.5 degrees. Without the moon, Gravitational interactions with the Sun and other planets would cause Earth's tilt to vary wildly over time, leading to extreme climate shifts. The Moon's presence has given Earth a stable environment for billions of years. It also drives the tides. Twice a day, the Moon's gravity pulls on Earth's oceans, creating bulges of water that move around the planet as it rotates. These tidal forces also affect the solid Earth, flexing the crust slightly, creating measurable deformations. But the tides also slow Earth's rotation. Energy from Earth's spin is transferred to the Moon, causing it to drift away. This process has been ongoing since the Moon formed. Early on, the Moon was much closer, perhaps 20,000 kilometers away instead of the current 384,000. Days were shorter, perhaps only 6 hours long. The Moon appeared enormous in the sky. Over billions of years, as the Moon drifted outward, days lengthened, tides weakened, and the Moon shrank in apparent size. This process will continue. Billions of years from now, Earth's day might be 50 hours long, and the Moon will be noticeably smaller in the sky. But this is so far in the future that it's nearly meaningless. The Sun will have begun its red giant phase by then, rendering Earth uninhabitable. The Moon's slow drift is just one of many processes playing out over timescales that dwarf human comprehension. The Moon's surface is ancient, scarred by billions of years of impacts. Unlike Earth, which has weather, plate tectonics, and erosion to erase craters, the Moon has no atmosphere, no water, no geological activity. Craters remain for billions of years, a record of every impact. The largest of these is the South Pole Aitken Basin, over 2,000 kilometers across and 8 kilometers deep, formed by a massive impact early in the Moon's history. Smaller craters dot the surface by the thousands, overlapping, erasing older features, creating a landscape frozen in time. The Moon has no magnetic field now, but it once did. Rocks brought back by Apollo astronauts show evidence of ancient magnetism, suggesting the Moon had a molten core billions of years ago. That core has since cooled and solidified, and the magnetic field faded. Without a magnetic field or atmosphere, the Moon's surface is exposed to solar wind, cosmic rays, and micrometeorite impacts. Over millions of years, these impacts have ground the surface rock into a fine dust called regolith. This dust covers the Moon to depths of several meters in places, a powdery, abrasive material that clings to everything. Walking on the Moon, as the Apollo astronauts did, leaves footprints that will last for millions of years. There's no wind to erase them, no rain to wash them away. They'll remain slowly degraded by micrometeorite impacts until the Sun's red giant phase destroys the Moon entirely. The far side of the Moon, often mistakenly called the dark side, is not actually dark. It receives just as much sunlight as the near side, but it's hidden from Earth. The Moon is tidally locked, meaning it rotates once per orbit, always showing the same face toward Earth. This wasn't always the case. Early in the Moon's history, it rotated faster, but tidal forces from Earth slowed that rotation until it matched the orbital period. Now, from Earth, we see only one hemisphere. The far side remained unseen until spacecraft orbited the Moon in the 1,960 seconds. The far side is different from the near side. It has fewer Maria, the dark basaltic plains formed by ancient lava flows. Instead, it's heavily cratered, dominated by highlands. The reason for this asymmetry is still debated. It may relate to the Moon's internal structure, or to the distribution of impacts, or to both. Mars, too, has moons, though they're nothing like ours. Phobos and Deimos are small, irregularly shaped, likely captured asteroids. Phobos orbits so close to Mars that it's slowly spiraling inward, In about 50 million years, it will either crash into Mars or be torn apart by tidal forces, forming a ring around the planet. Deimos, farther out, is more stable. It's tiny, just 12 kilometers across, a potato-shaped rock tumbling slowly in orbit. From Mars's surface, Deimos would appear as a bright star, not a disk. Phobos, closer, would rise and set multiple times a day, crossing the sky in just over 4 hours. These moons are curiosities small enough that their gravity is negligible. An astronaut on Phobos could jump off the surface and drift into space if they weren't careful. Escape velocity is only about 11 meters per second, slower than a sprinter. Venus and Mercury have no moons at all. For Venus, this might be due to its proximity to the Sun, whose gravity would destabilize a moon's orbit. Mercury is even closer, making a stable moon nearly impossible. Earth is fortunate to have the moon. It's unusually large relative to its planet, about 1/4 the diameter of Earth. No other terrestrial planet has such a massive moon. This has led some astronomers to refer to the Earth-Moon system as a double planet, two bodies orbiting a common center of gravity. Asteroids, those rocky remnants from the solar system's formation, come in many types. Some are metallic, made mostly of iron and nickel, fragments from the cores of shattered planetesimals. Others are rocky, composed of silicate minerals. Still others are carbonaceous, rich in carbon, water, and organic compounds. Studying asteroids helps us understand the early solar system. They're leftovers, unchanged for billions of years, preserving the conditions of the solar nebula. By analyzing their composition, we can piece together how planets formed, what materials were available, how the solar system evolved. Some asteroids are rubble piles, loose collections of fragments held together by weak gravity. Others are solid, monolithic rocks. A few have their own tiny moons, small rocks orbiting even smaller rocks, bound together in delicate gravitational dances. The largest asteroid, Ceres, is massive enough that its gravity has pulled it into a roughly spherical shape. It's classified as a dwarf planet, like Pluto. Ceres has a diameter of about 940 kilometers and may have a subsurface ocean of briny water. Ice has been detected on its surface, and bright spots, likely salt deposits, dot its craters. Visiting an asteroid is surprisingly difficult. They're small, with weak gravity, making it hard to land. Spacecraft that have attempted it often use harpoons or drills to anchor themselves. Even then, the surface can be unstable, covered in loose regolith that behaves unpredictably in low gravity. But we've managed. Missions like OSIRIS-REx and Hayabusa have collected samples from asteroids and returned them to Earth. These samples contain pristine material from the early solar system, grains that have never been altered by heat, water, or life. Studying them in laboratories reveals details about the sun's formation, the chemical composition of the solar nebula, and the processes that built planets. Every grain tells a story, if we know how to read it. Comets, those icy wanderers, are different from asteroids. They originate in the outer solar system, where temperatures are low enough for water, methane, and ammonia to freeze. When a comet's orbit brings it close to the sun, heat vaporizes these ices, creating a glowing coma and tail. The coma can be enormous, sometimes larger than the sun, though it's incredibly diffuse. The tail, pushed by solar wind and radiation pressure, always points away from the sun, creating the iconic curved streaks we see in photos. Comets are fragile, held together loosely by their own weak gravity. Some have broken apart under the stress of passing near the sun or a planet. Shoemaker-Levy 9, the comet that struck Jupiter in 1994, had already fragmented into over 20 pieces before impact. Each piece hit Jupiter's atmosphere at tens of kilometers per second, releasing energy equivalent to millions of nuclear bombs. Dark scars appeared on Jupiter's surface, visible from Earth through telescopes. Over weeks, these scars faded as Jupiter's winds mixed the debris into the surrounding atmosphere. It was a vivid reminder of the violence that exists in space, though such events are rare. Comets spend most of their time far from the sun, drifting quietly through the Kuiper Belt or Oort cloud. Only occasionally do they fall inward, brightening as they approach. Human history is filled with comet sightings, often interpreted as omens. Ancient civilizations saw them as harbingers of disaster or divine messages. In reality, they're just ice and rock, following the same physical laws as everything else. Halley's Comet, perhaps the most famous, returns every 75 to 76 years. Its orbit has been calculated backward through history, matching records from ancient China, Babylon, and Europe. The comet has been observed for over 2,000 years, appearing in artwork, literature, and historical texts. The next return of Halley's Comet will be in 2061. If you're young enough, you might see it. If not, others will, continuing a tradition of observation stretching back millennia. Space, for all its wonders, is inhospitable to life as we know it. There's no air, no water, no protection from radiation. Temperatures swing wildly from extreme heat and sunlight to extreme cold and shadow. And yet, humans have walked on the moon, lived aboard space stations, sent probes to every planet. We've adapted, built technologies to survive where we shouldn't. It's a testament to human ingenuity and determination. But space is not a place we're meant to conquer. It's a place to explore, to study, to understand, and in understanding it, we come to understand ourselves, our origins, our fragility, and our resilience. The solar system is finite but vast. Traveling from the Sun to Pluto at the speed of light would take over 5 hours. In a spacecraft moving at tens of thousands of kilometers per hour, it would take years or decades. Voyager 1, the fastest human-made object to leave the solar system, has been traveling for over 45 years and is barely beyond the heliopause. It will take tens of thousands of years to reach the distance of the nearest star. This is the scale we're dealing with. Distances that make interstellar travel, at least with current technology, impractical. We're confined to the solar system for now, and perhaps for a long time to come. But that's okay. There's so much to explore here. Moons with oceans, asteroids with water, planets with strange atmospheres. Each world is unique, each a puzzle waiting to be solved. And in solving these puzzles, we learn. We develop new technologies, new ways of thinking, new perspectives on what's possible. The challenges of space exploration drive innovation in ways that benefit life on Earth. The solar system has been our home for as long as we've existed. It will remain our home for as long as we survive. And when we finally venture to other stars, we'll carry the lessons learned here with us. For now, though, rest. Let the vastness of space settle around you, not as a weight, but as a comfort. You are part of something immense, something ancient, something beautiful. And in this moment, that's enough. Your breathing is slowing. Your body is sinking deeper into rest. The questions you've carried, the thoughts that have circled, all of them are fading, released into the quiet. There's nothing to hold on to, nothing to figure out, just the gentle pull of sleep, patient and kind. If you're still here, still listening, that's okay. There's no rush. Sleep will find you when it's ready. Until then, let yourself drift through these thoughts like clouds, soft and formless, carrying no weight. The universe is vast, but you are here, safe, warm, resting. The stars will continue to shine, the planets will continue to orbit, and you will continue to breathe slowly, softly, letting go with each exhale. Let's drift a little further before sleep finds you. There are more wonders to explore, more quiet truths to help settle your mind. Think about the nature of orbits. Every object in the solar system is falling, constantly, perpetually falling. But it's falling sideways, moving fast enough that the ground curves away beneath it at the same rate it falls. This is what an orbit is, endless falling that never ends in collision. Earth falls around the sun at about 30 kilometers per second. That's over 100,000 kilometers per hour. You're moving at this speed right now, as you lie here, though you feel completely still. The moon falls around Earth. The sun falls around the galactic center. Everything is in motion, always, held in balance by gravity and momentum. This can feel disorienting if you think about it too hard, but it can also be calming. You don't need to hold yourself in place. You're already where you need to be, held by forces far larger than yourself, carried along in patterns that have persisted for billions of years. Gravity itself is strange. It's not a force in the traditional sense, at least not according to general relativity. Instead, it's a curvature of space-time. Mass bends the fabric of space and time, and objects follow the curves created by that bending. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and smaller objects nearby roll toward it, not because they're being pulled, but because they're following the curvature of the sheet. This is analogous to how gravity works, though in 4 dimensions rather than 2. The sun creates a deep well in space-time, and the planets orbit along the curves of that well. They're not held in place by invisible strings. They're simply moving through curved space, following the straightest possible paths given the geometry around them. This might sound abstract, but it has real consequences. GPS satellites, for example, must account for the curvature of space-time near Earth. Time runs slightly faster in orbit than on the ground because space-time is less curved there. If GPS didn't correct for this, your navigation would drift by kilometers each day. Time itself is not constant. It flows at different rates depending on gravity and velocity. Near massive objects, time slows down. This has been measured and confirmed countless times. Atomic clocks on airplanes run slightly faster than clocks on the ground. Astronauts on the International Space Station age a tiny bit slower than people on Earth. These differences are minuscule, measured in fractions of a second over a lifetime, but they're real. Time is not the fixed, universal constant we often assume. It's flexible, malleable, dependent on where you are and how fast you're moving. On the surface of a neutron star, where gravity is so intense that a sugar cube-sized amount of matter would weigh as much as all of humanity, time would slow to a crawl relative to someone far away. A clock on the neutron star's surface would tick noticeably slower than one in orbit above it. We don't have neutron stars in our solar system, but we do have the sun, and even its gravity warps time slightly. Clocks on Earth run slower than they would in empty space, far from any star or planet. None of this affects your daily life. The differences are too small to notice without precise instruments, but it's a reminder that reality is stranger than it appears. The universe operates according to rules that don't match our intuition, and that's okay. We don't need to fully understand them to live within them. Black holes, though none exist in our solar system, are worth mentioning because they represent the extreme of what gravity can do. When a massive star exhausts its fuel and collapses, it can compress so much mass into such a small space that it creates a region from which nothing, not even light, can escape. The boundary of this region is called the event horizon. Cross it, and you're cut off from the rest of the universe forever. Time and space become so distorted that even the concepts start to break down. But black holes are not cosmic vacuum cleaners. They don't suck things in from afar. Their gravity, at a distance, is no stronger than the star that collapsed to form them. If the sun were replaced by a black hole of the same mass, Earth's orbit wouldn't change. We'd simply circle a dark, invisible object instead of a bright star. Of course, we'd freeze. The sun's light and heat are what make Earth habitable. Without them, temperatures would plummet, oceans would freeze, and photosynthesis would stop. But gravitationally, nothing would change. Orbits don't care about light or heat, only mass. Fortunately, the sun will never become a black hole. It's not massive enough. Black holes form from stars at least 20 times the sun's mass. Our sun will end its life as a white dwarf, a dense but stable ember slowly cooling over trillions of years. White dwarfs are strange in their own right. They're roughly the size of Earth but contain about half the sun's mass. A teaspoon of white dwarf material would weigh several tons on Earth. This density is supported not by normal pressure, but by quantum mechanics, specifically the Pauli exclusion principle, which prevents electrons from being squeezed into the same space. There's a limit to how much mass a white dwarf can hold. Beyond about 1.4 solar masses, electron degeneracy pressure fails, and the white dwarf collapses further, triggering a supernova, but most white dwarfs are well below this limit. They'll sit quietly, radiating away their remaining heat, eventually becoming black dwarfs, cold, dark, inert. Black dwarfs don't exist yet. The universe isn't old enough. Even the oldest white dwarfs are still faintly glowing. It will take trillions of years for them to cool completely, far longer than the current age of the universe. This is another example of cosmic timescales dwarfing human comprehension. Trillions of years. That's 1,000 billion, a million. Numbers so large they lose meaning. And yet, the universe is patient. It doesn't hurry. Stars burn for billions of years. White dwarfs cool for trillions. Galaxies drift apart for timescales beyond naming. There's no rush, no deadline, just slow, inevitable change. Back to our solar system. The asteroid belt, despite its reputation, is mostly empty. If you were standing on one asteroid, the next closest one would likely be too far away to see with the naked eye. The total mass of the entire belt is less than 4% of the moon's mass. And yet, there are millions of asteroids, ranging from grains of dust to dwarf planets. They orbit in a wide band between Mars and Jupiter, shaped by Jupiter's gravity into distinct groups and gaps. The Kirkwood gaps, for example, are regions where few asteroids exist, cleared out by orbital resonances with Jupiter. An asteroid orbiting in a Kirkwood gap would complete, say, 3 orbits for every one Jupiter completes. This resonance amplifies gravitational tugs, eventually nudging the asteroid into a different orbit. These patterns, created by gravity over millions of years, show how even seemingly chaotic systems have underlying order. The asteroid belt isn't random. It's structured, shaped by forces that operate slowly but relentlessly. Trojan asteroids share Jupiter's orbit, clustered at stable points 60 degrees ahead and behind the planet. These points, called Lagrange points, are locations where the gravitational pull of Jupiter and the Sun balance in just the right way to allow objects to remain stable. There are 5 Lagrange points for any two-body system. 3 are unstable, requiring constant adjustments to stay in place. 2 are stable, creating gravitational wells where objects naturally collect. The James Webb Space Telescope orbits one of Earth's Lagrange points, a spot about 1.5 million kilometers from Earth in the direction opposite the Sunday. From there, it has a clear view of deep space, shielded from the Sun, Earth, and Moon by a large sun shield. Lagrange points are useful for spacecraft because they require minimal fuel to maintain position. Objects there don't orbit a planet directly but move with it, held in balance by the combined gravity of 2 larger bodies. Nature discovered these points long before humans did. The Trojan asteroids have been there for billions of years, swept up and held in place by the same gravitational balance we now exploit for telescopes and satellites. Mars's two moons, Phobos and Deimos, are likely captured asteroids. They don't resemble our moon. They're small, dark, and irregularly shaped, covered in craters and regolith. Phobos orbits only 6,000 kilometers above Mars's surface, closer than any other known moon to its planet. It's so close that it orbits faster than Mars rotates, rising in the west and setting in the east. From Mars's surface, Phobos would zip across the sky in just over 4 hours. Tidal forces are pulling Phobos closer. Each orbit, it drifts inward by about 1.8 centimeters. In 50 million years, it will either crash into Mars or break apart into a ring. This is how some planetary rings may form. Saturn's rings, for example, might be the remnants of a moon that drifted too close and was torn apart by tidal forces. Or they could be material left over from Saturn's formation that never coalesced into a moon. The rings are beautiful but temporary. They're slowly spiraling into Saturn, pulled down by the planet's gravity and eroded by micrometeorite impacts. In another 100 million years, they may be gone, leaving Saturn a plain, ringless gas giant. But for now, they endure. Thin, bright, intricate, composed of countless icy particles ranging from dust, grains to boulders. Each particle orbits independently, creating wave patterns and gaps shaped by the gravity of Saturn's moons. The Cassini division, the largest gap in Saturn's rings, is nearly as wide as the distance from Earth to the Moon. It's not completely empty, but contains far fewer particles than the surrounding rings. The gap is maintained by gravitational resonances with Saturn's moon Mimas. These resonances are everywhere in the solar system, creating patterns, gaps, and clusters. They're evidence of gravity's patient, persistent influence, shaping orbits over millions of years. Uranus's tilt, 98 degrees from vertical, makes its seasons extreme. Each pole faces the sun for 42 years, then faces away for 42 years. Imagine a summer where the sun never sets, lasting longer than most human lifetimes, followed by an equally long winter of total darkness. Despite this, Uranus's atmosphere is relatively calm. Winds are moderate compared to Neptune. Temperatures are frigid but uniform, with little variation between the sunlit and dark hemispheres. This uniformity is puzzling. You'd expect extreme seasons to create extreme weather, but Uranus defies expectations. Heat is somehow distributed evenly around the planet, possibly by deep atmospheric currents or internal heat sources we don't yet fully understand. Neptune, by contrast, is stormy. Dark spots appear and vanish, high-speed winds circle the planet, and bright clouds form at high altitudes. All this activity despite receiving less sunlight than Uranus. The energy driving Neptune's weather comes from within. The planet emits 2.6 times more energy than it receives from the Sunday. This internal heat, left over from its formation and possibly supplemented by ongoing gravitational compression, keeps Neptune's atmosphere active. Neptune's moon Triton is one of the most intriguing objects in the solar system. It orbits backward, opposite Neptune's rotation, and in a perfectly circular path. This suggests it wasn't formed alongside Neptune, but was captured from the Kuiper Belt. Triton is geologically active. Nitrogen geysers erupt from its surface, shooting plumes several kilometers high. These geysers suggest internal heat, possibly from tidal forces or residual warmth from its capture. Triton's surface is young, with few craters, indicating recent resurfacing. Parts of it resemble cantaloupe skin, a strange texture created by processes we don't fully understand. Being captured wasn't gentle. Triton's current orbit is the result of billions of years of tidal interactions with Neptune. Its original orbit was likely highly elliptical, taking it far from Neptune and then swinging close. Over time, tidal forces circularized the orbit, heating Triton's interior in the process. Eventually, Triton will spiral inward and be destroyed, torn apart by Neptune's gravity. But that won't happen for hundreds of millions of years. For now, it remains a captured interloper, slowly succumbing to the planet that claimed it. The Kuiper Belt, beyond Neptune, is home to thousands of known objects and likely millions more. Pluto is the most famous, but it's just one of many similar-sized bodies drifting in the cold outer reaches. These objects are pristine, unchanged since the solar system's formation. Studying them reveals details about the solar nebula's composition, the processes that built planets, and the conditions in the early solar system. Some Kuiper Belt objects have eccentric orbits, bringing them close to the Sun periodically. These become comets, their ice is vaporizing as they warm, creating the glowing displays we occasionally see from Earth. Others remain distant, never approaching the Sun, drifting in cold darkness for billions of years. They're silent, patient, witnesses to the solar system's entire history. The Oort cloud, even farther out, is hypothetical. We've never directly observed it, but comets with extremely long orbital periods suggest a vast shell of icy objects surrounding the solar system, extending halfway to the nearest star. If the Oort cloud exists, it contains trillions of objects, most smaller than a kilometer across. They're so far from the Sun that they barely feel its gravity. A passing star could disturb them, sending some inward on long, slow falls toward the inner solar system. Such events are rare, but have likely happened many times over the solar system's history. They might explain periodic increases in comet activity, though proving this requires observations spanning longer than human lifetimes. The solar system's edge, wherever you define it, fades gradually into interstellar space. There's no wall, no boundary, just a slow transition from the Sun's influence to the background of the galaxy. Voyager 1 and 2 have crossed the heliopause, leaving the Sun's protective bubble. They're now in interstellar space, surrounded by gas and magnetic fields from other stars, no longer dominated by the Sunday. Yet even there, the Sun's gravity still holds them. They orbit the galactic center along with the Sun, moving through space as part of the Sun's extended family. They'll never truly leave. Gravity's reach is infinite, weakening with distance but never vanishing entirely. These probes will drift for millions of years, possibly billions, long after the Sun has died and the planets are gone. They're monuments to human curiosity, messages in bottles cast into an ocean we're only beginning to explore. And that's where we are, on a small planet orbiting an ordinary star, looking outward, asking questions, seeking to understand. The solar system is our home, our laboratory, our classroom. It's not designed for us. It's indifferent to our existence. But it's also where we learn to ask questions, to build tools, to imagine possibilities beyond our immediate surroundings. Every fact you've heard tonight, every phenomenon described, is a piece of a larger puzzle, and we're still putting it together, one discovery at a time. But for now, rest. Let these thoughts settle like dust. There's no need to remember any of this. Just let it wash over you, a gentle tide of information that quiets the mind rather than filling it. Your breath is deep and slow. Your body is heavy, sinking into the surface beneath you. The universe continues, vast and patient, and you are part of it, small and safe, drifting towards sleep. There's nothing to solve tonight, nothing to decide, just this quiet moment, this gentle release, this soft surrender to rest. If sleep hasn't found you yet, that's okay. It will come. It always does. Until then, let yourself be still. Let the silence hold you. Let the darkness be a comfort rather than a concern. You are exactly where you need to be. The cosmos doesn't need your attention. It will continue without observation, and you can let go, knowing that everything is as it should be. Before we close, let's drift through a few more quiet truths about our cosmic home, gentle thoughts to carry you into rest. Consider the emptiness of space, between atoms, between planets, between stars. There is vastness. If an atom were the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be smaller than grains of dust orbiting at the stadium's edge. Everything else would be empty space. This means that matter, including you, is mostly emptiness. The atoms in your body are separated by distances that are enormous relative to their size. You feel solid, but at the atomic scale, you're mostly space held together by electromagnetic forces. This isn't unsettling. It's simply the nature of physical reality. Solidity is an illusion created by forces, not by matter pressed tightly together. And those forces are strong enough, reliable enough, that the illusion never fails under ordinary circumstances. The electromagnetic force, the one that holds atoms together and makes matter feel solid, is much stronger than gravity. It's about 36 times stronger, an incomprehensibly large number. Gravity is weak by comparison, so weak that you can overcome Earth's entire gravitational pull by picking up a paperclip with a small magnet. And yet, gravity shapes the universe. It holds planets in orbit, binds galaxies together, and curves space-time. It wins not through strength, but through persistence and scale. Gravity adds up. Every particle of matter contributes, and over large distances, those contributions become dominant. Electromagnetic forces, by contrast, cancel out at large scales. Positive and negative charges balance, leaving objects electrically neutral, but mass only adds, never subtracts. Everything has positive mass, and more mass means more gravity. This is why stars form. A cloud of gas, left alone, will slowly collapse under its own gravity. As it collapses, it heats up. Eventually, if the cloud is massive enough, the core becomes so hot and dense that hydrogen begins fusing into helium. A star ignites, and gravity is balanced by the outward pressure of fusion. This balance can last billions of years. For the Sun, it's been stable for over 4 billion and will continue for another 5 billion. During that time, the Sun converts about 4 million tons of matter into energy every second, following Einstein's famous equation, E = mc squared. 4 million tons sounds like a lot, but the Sun has about 2 billion tons to work with. It's burning through its fuel slowly, at a rate sustainable for eons. When the fuel finally runs out, the balance will shift. The core will contract, heating up enough to fuse helium into carbon and oxygen. The outer layers will expand, cooling and reddening, as the Sun transforms into a red giant. This phase will last only a few 100 million years, brief compared to the Sun's main sequence lifetime. Eventually, even helium fusion will cease. The outer layers will be gently blown away, creating a planetary nebula, and the core will cool into a white dwarf. This is the life cycle of a star like the Sunday birth, a long, stable life, a brief dramatic old age, and then quiet fading. Larger stars live faster and die more violently. Smaller stars burn slowly, living for trillions of years. The smallest stars, red dwarfs, are so efficient that they'll still be shining long after the Sun is gone. Some red dwarfs formed early in the universe's history are only now reaching middle age. They'll outlast every other type of star, burning faintly but steadily for trillions of years. The universe is about 13.8 billion years old. In another trillion years, it will be a very different place. Most stars will have exhausted their fuel. Galaxies will have drifted apart, carried by the expansion of space. Star formation will slow and eventually stop as gas is locked up in dead stars and planets. Eventually, the only stars left will be red dwarfs, slowly fading. After they go out, the universe will be dark, illuminated only by the faint glow of white dwarfs and the occasional collision or decay event. This is called the degenerate era, a time when the universe is dominated by compact objects like white dwarfs, neutron stars, and black holes. It will last for quadrillions of years, far longer than the current age of the universe. Beyond that lies the black hole era, when even compact objects have decayed or been consumed, and black holes are the last remaining structures. These, too, will eventually evaporate through Hawking radiation, a quantum process that allows black holes to slowly lose mass. The largest black holes, those at the centers of galaxies, will take 100 years to evaporate. That's a 1 with 100 zeros after it, a number so large it's hard to conceptualize. And yet, even that is finite. Given enough time, black holes will vanish, leaving behind only radiation. After that comes the dark era, when the universe contains only dilute radiation, spreading ever thinner as space continues to expand. There will be no stars, no planets, no structures of any kind, just photons, neutrinos, and possibly other particles drifting through infinite space. This is the ultimate fate of the universe according to current understanding. Not a dramatic end, but a slow fade into darkness and cold. Entropy increases, complexity decreases, everything trends toward equilibrium. But this is so far in the future that it's almost irrelevant. The timeline between now and then dwarfs the timeline between the Big Bang and now. We live in an early, vibrant phase of cosmic history, when stars are still forming, galaxies are still bright, and complexity is still possible. For now, the solar system is full of activity. The sun shines, planets orbit, moons drift, asteroids tumble, comets fall, and on one small planet, life thrives, adapts, and wonders about its place in the cosmos. This moment, right now, is fleeting on cosmic scales. The configuration of the solar system will change. Planets will migrate slightly. The sun will evolve. Eventually, everything familiar will be gone. But fleeting doesn't mean meaningless. Every moment exists, fully and completely, even if it doesn't last. The fact that things change doesn't diminish their reality. It simply means that now is precious, a unique arrangement that will never be exactly repeated. You exist in this moment, in this place, part of a universe that has been unfolding for 13.8 billion years. The atoms in your body are older than the Sunday. The calcium in your bones was forged in a supernova. The iron in your blood was created in the core of a massive star. You are, quite literally, made of stars, not metaphorically, but physically. Every element heavier than helium in your body came from stellar processes. You're built from the remnants of dead stars, recycled through the galaxy and eventually assembled into a living, thinking being. This connection to the cosmos is profound. You're not separate from space, observing it from outside. You're part of it, a localized, temporary concentration of matter that happens to be capable of thought. And thought itself is remarkable. The universe contains countless atoms, but only a tiny fraction are arranged in ways that allow for consciousness. In you, the universe has become aware of itself, able to reflect on its own existence. This awareness is rare, as far as we know. We found no evidence of other intelligent life. We may be alone, or we may be one of countless civilizations scattered across the galaxy. Either possibility is profound. If we're alone, then consciousness is an extraordinarily rare occurrence, a fragile flame that exists only here, on this small planet. The universe is vast and mostly unconscious, with awareness concentrated in one unlikely corner. If we're not alone, then life is robust, emerging wherever conditions allow. The universe might be teeming with life, though distances are so vast that contact may be impossible. We might live in a cosmos full of civilizations, each isolated by the sheer scale of space. Either way, you're here. You're part of this grand experiment, this unfolding story of matter organizing itself into ever more complex forms. And for tonight, that's enough. Let your mind release these thoughts. They've served their purpose, carrying you through the solar system, from the sun to the farthest reaches, touching on gravity, time, light, and the nature of existence itself. None of this requires your effort or attention now. The universe will continue whether you're awake or asleep, whether you're thinking about it or not. It's indifferent to your awareness, and that indifference is a kind of freedom. You can rest knowing that nothing depends on you tonight. The planets will orbit, the stars will shine, the cosmos will unfold according to the laws of physics, patient and inevitable. Your breathing is steady and slow. Your heartbeat is calm. Your muscles are relaxed, releasing tension with each breath. The weight of your body sinks into the surface beneath you, supported and safe. There's no need to think anymore. No need to understand or remember. Just this quiet, this stillness, this gentle drift into the darkness of sleep. If thoughts arise, let them pass like clouds. They don't need your attention. They're just noise, echoes of the day, remnants of activity that no longer serves you. Sleep is near now, patient and kind, waiting for you to let go fully. It's been part of you since the beginning, a biological necessity, a daily return to unconsciousness where your body heals and your mind processes. Trust it, surrender to it. There's nothing to fear in sleep, only rest and renewal. The solar system continues its slow dance, the planets tracing their ancient paths, the sun burning steadily at the center. And you, small and safe on this small planet, are part of that dance. Moving through space at thousands of kilometers per second, held in place by gravity, warmed by starlight. It's a beautiful arrangement. This temporary configuration of matter and energy that allows for life, for thought, for rest, and you're experiencing it right now, in this moment of quiet transition between waking and sleep. Let yourself go, let the universe hold you, let the darkness be a comfort. The night sky above, whether you can see it or not, is filled with points of light. Each star is a sun, perhaps with its own family of planets. Each galaxy contains billions of stars, and there are billions of galaxies, spread across distances so vast they challenge comprehension. All of it moves in silence, following the laws of gravity and motion, unchanging in its fundamental nature, yet constantly evolving in its details. Stars are born and die, galaxies merge, space itself expands, carrying everything farther apart. And yet, here you are, a conscious observer in a universe that doesn't require consciousness to exist. You're an unlikely event, a fortunate arrangement of atoms, experiencing a brief moment of awareness in the midst of cosmic time. Cherish it, but don't cling to it. Let this moment be what it is, a quiet pause, a gentle transition, a soft ending to the day. Your eyes are heavy, your thoughts are fading. The boundary between waking and sleep is blurring, becoming indistinct. Cross that boundary when you're ready. There's no rush. Sleep will wait for you, patient as the stars, constant as gravity, inevitable as time. And when you wake, the solar system will still be here, unchanged in its essential nature, continuing its slow journey through the galaxy. The sun will rise again, the planets will orbit, and you'll begin another day, refreshed and renewed. But for now, rest, let go, drift away. Thank you for drifting through this journey with me tonight. May you rest deeply and wake gently. May your dreams be soft and your sleep be sound. Good night.